Hello my student, we're gonna start with chapter 1, Introduction to Machinery Principles. Section 1.5, Faraday's law induced voltage from a time-changing magnetic field. The first major effect to be considered is called Faraday's law. It is the basis of transformer operation. So Faraday's law states that if a flux passes through a turn of a coil of wire, a voltage will be induced in the turn of wire that is directly proportional to the rate of change in the flux with respect to the time. So we can write equation E induced is equal what? Minus d flux over dt. D flux over what? dt. Next slide. Where E induced is the voltage induced in the turn of the coil, and flux is the flux passing through the turn. If a coil has n turns and if the same flux passes through all of them, then the voltage induced across the whole coil is given by E induced equal minus n d flux over what? Over dt. So if we have number of turns, we can just write n here. So n is what? Number of turns of wire in a coil. E induced, voltage induced the coil, and flux passing through the coil. Next slide. So the minus sign in the equations is an expression of Lenz's law. So let's define Lenz's law here. Lenz's law states that the direction of the voltage build up in the coil is such that if the coil ends were short circuited, it would produce current that would cause a flux opposing the original flux change. It is left out of Faraday's law in the remainder of this book. We have a figure here, guys. We can see that we have this is a coil inclosing increasing magnetic flux here. This is the original flux we have. So we will have another flux which is opposing the increasing of the original flux. This is the flux here. Okay, opposing the increasing. Okay, guys. Now let's move to the next slides. Let us solve an example here. Example 1.6. Figure 115 shows a coil of wire wrapped around an iron core if the flux in the core is given by the equations. This is the flux we have, equal 0.05 sine 377 Weber. If there are 100 turns on the core, what voltage is produced at the terminals of the coil? Of what polarity is the voltage during the time when the flux is increasing in the reference direction shown in the figure? Assume that all the magnetic flux stays within the core. So it's mean what? Assume that all the flux leakage is 0. We don't have any leakage for the flux here. This is the induced, and this is the core here. This is the core, and we have here the flux passing through the core. We have a number of turns here, 100 turns. Okay, so now let us apply the equations to solve this example here. Just we can write here, guys, E induced is equal what? N d flux over what? Over dt. Okay, we have how many turns we have? We have 100 turns. Okay, multiply d over dt. Okay, we have the flux. It is giving from the question, which is here 0.05 sine 377 t. Okay, so let's make the derivative for the value of the flux here. You will just multiply 377 multiply with 0.05 and then multiply with 100. Okay, so the answer will be 1885 cosine with the same angle here 377 t. So this is the answer for this example. Okay, let's solve another questions we have here. Question number 1. The field coils of a 6-pole DC generator, each having 500 turns, are connected in series. When the field is excited, there is a magnetic flux of 0.02 Weber per pole. If the field circuit is opened in 0.02 second and residual magnetism is 0.002 Weber per pole, calculate the average voltage which is induced across the field terminals. In which direction is this voltage directed relative to the direction of the current? Okay, I will open new page to solve this example now. So we have to find total number of turns. So n equal what? 6 multiply 500. So we have here 3000. Okay, then the total initial flux, we'll try to find the total for all the flux we have. For initial flux now, initial flux total equal what? 6 number of poles multiply 0.02. The answer will be 0.12 Weber. Total for residual flux is equal now 6 pole multiply 0.002. The answer will be 0.0112 Weber. So the change in the flux, now d flux, we'll take the difference between the initial and residual, 0.12 minus 0.012, the answer will be 1 or 0.108 Weber. Now we will also we have the dt time of opening the circuit, dt equal what? 0.002 second. Now we'll apply the formula here. EMF, electromotive force or induced, is equal what? N multiply the flux over dt. So we have total number of turns, which is 3000 multiply 0.108 over 0.02. So the answer will be 16,200 volt. This is the final answer for the problem. Let's go back to our slides here now. Question 2 you can try to solve. Okay, it's very simple. We will use the same formula. Now let's move to the new section 1.6, production of induced force on a wire. A second major effect of a magnetic field on its surroundings is that it induces a force on a current carrying wire within the field. The basic concept involved is illustrated in the figure. Next figure, we have what? F equal ILB, where I here magnitude of the current, L length of the wire, with direction of I defined to be in the direction of the current flow, B magnetic flux density vector. The direction of the force is given by what? By the right hand rule. Okay, the magnitude of the force is given by the equation. If we have an angle here, we can write what? Sine theta. ILB sine theta, where theta is the angle between the wire and the flux density vector. This is the here the right hand rule. Thumb will be the direction of for the current, and fingers will be magnetic field here, and the palm will be for the force out of the page here. Okay, this is the right hand rule. Next slides here. Now let's solve example 1.7. Figure 1.16 shows a wire carrying a current in the presence of a magnetic field. The magnetic flux density is 0.25 Tesla directed into the page. If the wire is 1 meter long and carries 0.5 ampere of current in the direction from the top of the page to the bottom of the page. Okay, this is the direction of the current from the top to the bottom of the page. Okay, what are the magnitude and direction of the force induced on the wire? Okay, so we'll apply the formula here. If we have equal what? ILB LB sine theta. Okay, so the current we have 0.5 ampere multiply 1 meter long for the wire, multiply magnetic field 0.25 Tesla, 0.25 Tesla, and multiply the angle here. Sine theta is here 90 degree. Okay, 90 degree, as you can see from the figure. So the answer will be what? The answer will be 0.125 Newton. Okay, what about the direction? Directed the force will be directed to the right. Okay, by using the right hand rule we can find the direction for the force. Let's move to the next slide. Section 1.7, induced voltage on a conductor moving in a magnetic field. If a wire with the proper orientation moves through a magnetic field, a voltage is induced in it. This idea is shown in the figure. The voltage induced in the wire is given by the formula here. We have E induced is equal V multiply P multiply I, where V, this is velocity of the wire, P magnetic flux density vector, and L length of the conductor in the magnetic field. Okay, vector I points along the direction of the wire toward the end, making the smallest angle with respect to the vector V multiply B. And you can see this is the field, direction of the field, and this is the motion V, and this is AMF or current here. Okay, right hand rule. Now let's solve an example here. Example 1.8 shows, figure 117 shows a conductor moving with a velocity of 5 milli per second to the right in the presence of a magnetic field. This is the direction here. The flux density is 0.5 Tesla into the page. So this is the direction here, into the page. X is mean into the page. If it is dot, that's mean out of the page. Okay. And the wire is 1 meter in length, oriented as shown. What are the magnitude and polarity of the resulting induced voltage? Okay, be careful, we are talking about now polarity because we are talking about what the voltage. Again, here we will apply the formula to solve this example. Okay, so E induced is equal what? V multiply P multiply length. Okay, so always VB will be what? Between sine 90. Okay, multiply L length of the conductor will be cosine, always cosine. Okay, so here there is no angle, so cosine 0. Okay, so we will have what? Sine 90 is 1, cosine 0 is 1, so we'll have what? VBL. Okay, just will apply now, substitute for V5 multiply 0.5 Tesla multiply 1 meter length. The answer will be what? 2.5 volt. Okay, so thus the induced voltage is 2.5 volt, positive at the top of the wire. Okay, positive at the top of the wire. we will use the same right hand rule. We can find the polarity. Okay, it will be clear. Positive at the top and negative at the bottom. This is another example here. Now we have what angle here, 30. Example 1.9. Figure 118 shows a conductor moving with a velocity of 10 millisecond to the right in a magnetic field. The flux density is 0.5 Tesla out of the page. This is now out of the page. And the wire is 1 meter in length, oriented as shown. What are the magnitude and polarity of the resulting induced voltage? We can apply direct the formula here. E induced is equal what VB sine 90 multiply what L cosine how much we have here now, 30. Okay, between the conductors and the vector VB. We'll just substitute now 10 multiply 0.5 multiply 1 multiply cosine 30. So the result will be 4.33 volt. This is the answer. What about the polarity? Will be this voltage in a wire moving in magnetic field is what fundamental to the operation of all type of generators. So the positive will be at the bottom here by using right hand rule. Here we have problems you have to try to solve. 3 problems, 1.9, 1.10, 1.11, and with the figures here. Just try to solve. Okay, and I will send you the solution. Now the last section in this chapter 1.8, the linear DC machine as a simple example. A linear DC machine is shown in the figure 119. It consists of a battery and a resistance connected through a switch. This is the battery, this is a switch here we have, and we have a resistor here. Okay, this is connected through a switch to a pair of smooth frictionless rails. Along the bed of this railroad track is a constant uniform density magnetic field directed into the page. This is the magnetic field into the page. A bar of conducting metal is lying across the tracks. Its behavior can be determined from an application of the 4 basic equations to the machines. We will use the 4 basic equations that we have discussed. Okay, the first one is for the equations for the force. Here we have F equal I multiply L B. The second equation is for the voltage induced on a wire, E induced equal VB multiply I. The third one is Kirchhoff voltage law for the machine, VB minus IR minus E induced equals 0. And the fourth one is Newton's law for the bar across, F net equal M multiply mass. Okay. Now let's start starting the linear DC machines. Okay. Closing the switch produce a current flow I equal VB over R. The current flow produces a force on the bar given by FILB. The bar accelerates to the right, producing an induced voltage as it speeds up. The induced voltage reduces the current flow I equal VB minus E induced over R. The induced force is thus decreased. Okay, F equal I decrease over lb until I eventually f equal here 0. At that point, E induced equal VB, I equal 0, and the bar moves at a constant no load speed. VSS, this is steady state speed, VB over PL. Again, here for the linear DC machine as a motor, here you have to follow the steps here again. Okay, so a real DC motor behaves in an analog fashion when it is loaded. As a load is added to its shaft, the motor begins to slow down, which reduces its internal voltage, increasing its current. Now, the increased current flow increases its induced torque, and the induced torque will equal to the load torque of the motor at a slower speed. The power converted from electrical form to mechanical form in a real rotating motor is given by this equation: P equal torque induced multiply angular speed. Here the linear DC machine as a generators. Again, we have to apply the same equations here. Okay, so a real DC generator behaves in this manner. A torque is applied to the shaft in the direction of the motion. The speed of the shaft increases, the internal voltage increases, and the current flows out of the generators to the loads. The amount of mechanical power converted to the electrical form in a real rotating generator is given by these equations: P converted equal torque induced multiply angular velocity. Okay, it is interesting that the same machine acts as a both motor and generator. The only difference between the two is whether the externally applied forces are in the direction of the motion. If it is in the direction of the motion, it will be generator, or opposite to the direction of the motion, it will be what? Motor. Or electrically, when E induced greater than VB, the machine acts as a generator, and when E induced is less than VB, V battery, the machine acts as a motor. Now we have an example here, example 110. Okay, we'll just solve this example. Okay, the linear DC machine shown in figure 127 has a battery voltage of 120 volt, an internal resistance 0.3 ohm, and a magnetic flux density 0.1 Tesla. Okay, so A, what is the machine's maximum starting current? What is its steady state velocity at no load? Okay, so we'll try to solve the first part here. So we can find the current by using what? Ohm's law. Okay, I is equal what? Vp minus E induced, okay, over R. Vb 120 minus 0 over what? 0.3. It will be 400 ampere. So when the machine reaches steady state, so it's mean what? F induced is equal what? 0, and I equal what? 0. Therefore we can say that Vb is equal what? E induced. induced equal what? VSS steady state BL. Okay, so we to find VSS now is equal what? V battery over BL, 120 over 0.1 multiply 10 meter. It will be what? 120 millisecond per second. Okay, this is the solution for part A. Now let's come to the next part. Okay, for B. Okay, B, suppose that a 30 Newton force pointing to the right were applied to the bar. What would the steady state speed be? How much power would the bar be producing or consuming? How much power would the battery is producing or consuming? Explain the difference between these two figures. In the machine, is the machine acting as a motor or as a generator? Okay, we can check the figures here, guys. This is now for B. Okay, B, change the color. This is B now. Applied force to the right. This is the force here. Okay, if applied 30 Newton, so we will have what? If induced to the left. Okay, with the same value, 30 Newton. Okay, now we can say that for B, okay, so if applied will equal what? If induced equal ILB. Okay, we can find the current. I is equal what? If induced over what? LB equal what? 30 Newton over 10 multiply 0.1. Okay, so the answer will be 30 ampere. Following up through the bar. So induced voltage on the bar must be, now we induced, is equal VB plus what? IR. Okay, Kirchhoff voltage law is equal 120 plus what? 30 multiply 0.3. So it will be 129 volt. Okay, now the final steady state, it will be VSS equal E induced over BL. We same the same voltage here, 129 over 0.1 multiply 10. The answer will be what? 129 millisecond. Okay, it is clear, guys, from the voltage now that the machine in this case will act as a generator. Okay, because we have now E induced is greater than what? VB. Induce here at this case is greater than what? VB. Okay, so it is what? Generator. Let's now come to the part C. It will be the same procedure, guys. Okay, it will be the same. We'll have to follow the same steps here. Now see, now suppose a 30 Newton force pointing to the left. Okay, now to the left were applied to the bar. What would the new steady state speed be? Is the machine acts as a motor or generator? As you can see from the figure now, now to the left here, if load 30 Newton, we will have what? If induced opposing the F load. Okay, 30 Newton. Now for C, we'll apply the same steps here. If applied is equal what? To if induced. If induced, okay, equal ILB. I equal what? If induced over what? LB. 30 over what? 10 multiply 0.1, so it will be 30 ampere. Now in this case, now A induced is equal what? VB minus IR. Okay, because now it is what? Motors here, it will be what here? Minus. Okay, if it is to the left applied, it will be minus. Okay, for B it was positive because a generator. Okay, so 100 equal 100 minus what? 30 multiply 0.3. The answer will be what? 111 volt. Okay, 111 volt. Now VSS now steady state, the same here, will be what? Equal E induced over what? BL, equal here 11 volt over 0.1 multiply 10. Now the answer will be 111 millisecond, meter per second. Okay, now it is clear from the answer here. Okay, that V induced, E induced here is what? Less than what? VB. So it will be what? The machine will act as a motor. Okay, so this is the end for this example, and here you can find two problems, problem 21 and what? Problem 22. Okay, you can solve and make more practice. Okay, and we'll send you the solution. This is the end for this chapter. See you inshallah next new chapter. Thank you.